and go through example problems you want to work on. We've got a couple days left before the actual final. We have all 4 days, right? Days 3, 4, 5, 6. So we have 4 days of review coming up. And it's kind of open-ended. It's up to you guys to ask which you want to go over. If you want to take a minute, you could, if you have your old tests, if you look at them, I recommend, I didn't mention this last week, I didn't see you guys on Friday, or day 2, but maybe starting tomorrow, bring your old tests and fold with you every day. So that when we're reviewing it, you're able to look at your old tests, you're able to look at your stuff and say, oh, I got this wrong, I should ask this kind of question. And what you should really do is, over the next few nights, is at night, practice some problems and see what you want to go over with me. What's something that you want to work on, a topic? Something that you struggled on either recently, like on this last test you just got back, or on something 2 units ago. But try to focus on semester 2, although obviously you could ask about semester 1 because it does kind of come up inherently. And it could be an exact question you ask, or you could just say, hey, I need help with this topic. Or even if you don't even know what topic it is, what section, because I haven't looked with you, so I can just go up to example problems in that section. What do you want to do? What do you want to do? Alex, shoot.
How to find the slant asymptotes?
Slant asymptotes?
Yeah.
Okay. So if we're looking at asymptotes in general, we have the degrees that are important. So we look at the degree of the numerator and the denominator first, okay? That's the first thing we do. And we recognize we have 3 cases. If the degree of the numerator is greater than the degree of the denominator. For example, 2x squared plus 5x minus 4 over x plus 2. If that's the case, we have a slant asymptote. Okay, we have a slant asymptote. Now, there are 2 other cases, Alex, where we have horizontal asymptotes. I'm going to go over this example, and then I'm just going to mention those other cases so you know. So if we want to find the slant asymptote of this, what should we do to find the slant asymptote? Yeah, long or synthetic division, depending on what you have. Here, I would use synthetic because you have x plus 2 in the denominator. So I would just run this through synthetic. 2, 5, negative 4, and then you're technically dividing by x plus 2, so it's like putting a negative 2 out here. If you remember when we did synthetic division, when you divided by something, it was in the form x minus c, so this has to be the opposite of whatever that number was. So we take that opposite of that number, put it up here, and run it through our table. Now, when we do that, we start by bringing down this 2 right here first. Negative 2 times 2 is negative 4. Negative 4 plus this 5 is going to give me positive 1. Then I do it again. Now, I don't really need to do the next step, but I'm going to do it anyway. Negative 2 times 1 is negative 2. Negative 2 and negative 4 is negative 6. Well, this is the remainder over here. I don't care about the remainder. Remember, the remainder doesn't matter when we're looking for the slant asymptote. The remainder is like the y-coordinate. If I were looking at a graph, if you remember, that was the whole concept there with polynomials. This was the y, this was the x-coordinate you plug in, this was the y-coordinate. But this is not, we're not doing that. We're looking at rational functions. So this is the piece of information that's useful, this 2 and this 1. So we look at this and we realize, well, we're dividing something that's squared, right? This term is squared up here, divided by something that's linear. Squared divided by linear results in linear, meaning x to the first power. So this becomes 2x plus 1. And that's the information we pull from this. So this is my slant asymptote. Y equals 2x plus 1. Okay? I went over the theory behind this in section E2, and I went into like the actual idea behind, if you think about plugging in infinity, this is really a remainder, this is like negative 6 over x plus 2. And when you plug infinity into that, it drops off, it goes to 0, and I showed why the remainder doesn't matter. But if you want to know just the skill of how to do it, synthetic division, the result you get without the remainder is your slant asymptote. Okay, the other 2 cases, who can discuss those other 2 real quick? So this is if the numerator was greater than the denominator. That's case 1. How about this one? When they're equal. How about this one? Yeah. Inigo, what would you do?
So just starting with the last one. So the
I'm asking about the horizontal or slant asymptotes. What would this case be?
so since the degree of the numerator equals the degree of the denominator, you just take the ratio of the leading coefficient.
Yeah, you do y equals whatever this ratio is. So that one would just be 2/3, and that would be a horizontal asymptote. And then the third case is similar, except now we have the degree of the numerator being less than the degree of the denominator, i.e. y equals 7 over x plus 5. The degree of the numerator would be 0. The degree of the denominator would be 1. So the numerator has less degree than the denominator. And what would this one result in? Chandler?
Y equals 0.
Yeah, horizontal asymptote, y equals 0. And that's always the case. So we have three cases. Slant asymptote from synthetic, horizontal from the ratio of the coefficients, or horizontal and the x-axis itself, y equals 0. Those are the three cases of asymptotes for rational functions. Question, Alex. What else? Inigo.
Well, I don't have like a specific question, but just like the second quarter project,
The second quarter project. Remind me which one that was again.
like when you have a bicycle factory.
It's not going to be on your final exam. No, only because that's the thing that we did in this class, and the final is both classes. They didn't do projects in that class, so it wouldn't be a question on your final. I think I made it a question on your midterm, correct?
Mm-hmm.
Yeah, because your midterm we had like 5 or 6 questions different between our classes. It won't be that way for this. If you're unsure what to ask, you should be looking at like either the names of the topics in your notes, maybe open up the textbook and look to see what problems are like, oh wow, I remember how to do this. Opening up the problem sets and looking at those solutions, that might help. Yeah.
Maybe like when you have the acid problem, like if you have a
Sure. Mixtures?
Yeah.
Yeah. Jeff, can you do me a favor? Could you open that window? Just the blinds on the window? To let a little bit of air in the room. All right, so let's take a look at any sort of mixture problem, right? It doesn't have to be acid, by the way, any mixture problem. So this is a problem about concentration, not your concentration, but the concentration of the substance. It's the concept of density, if you think about it. If something is more weighted than the other thing, there's more density than the other thing. Well, it's like a weighted average for a test. Your tests are not equally weighted, you know that, right? Like your last test, how many points was that? 35. The previous one was at 40, right? So which one's actually worth more? Yeah, the one at 40. How much more? Well, you have to do a weighted average to see. So you have to sum together all your points, divide by all the points possible, and get the total average. Well, in reality, then, it makes some of the tests worth more than the others. That's what you're doing here, actually. So you've got a fluid with more density of some sort of solute. You've got another fluid with less density than the other one of that same solute. So maybe I'm mixing salt water of like 80% salt water with 60% salt water. If I want to get 70% salt water, what should I do? It's pretty easy, right? I got 80% salt water and 60%. And I want 70% salt water. What do I do? Equal amounts of both. I don't care how much, just they gotta be equal, right? If you're looking for the midpoint of a solution, you have to put equal amounts of both. It makes sense logically. Well, the problem is now, what happens when you need 72% of that solution, right? Or 72% salt for that new solution. So let's use that as an example. So we've got 60% salt solution. We've got 80% salt solution. And we want to mix them together to achieve 72% salt solution. And let's say we want how much of this? What should we say? How much? Give me a volume. How much of the final solution should we make? Jeff, give me a volume. 1,000 milliliters, that works. That's an easy number to work with, right? That works out well. So we need 1,000 milliliters of this solution at the end. That's our goal. Now, remember, let me just point this out. I could give you the amount of milliliters we have of the 60% and tell you how much of the 80 should be added to make a 72%. I didn't do that though. I gave you the final volume. I could give you an initial volume of one of the other two, and then the final volume is just x plus whatever that initial volume was. So I'll vary that at the very end. We'll see how that would change the table, okay? So the way I had you guys do this was to think about it with a table. You don't have to use a table if you don't want to. Some of you preferred not to, and I noticed in the test a few did not, so you don't have to. You could just say to yourself, all right, well, you know, if I'm going to make x of this solution, I'm going to make 1,000 minus x of this solution. And is that logical right away if you think about it? If I have 700 milliliters of one solution, how many do I have for the other then? 700, and what makes 1,000? 300. So I'm just taking 1,000 minus off the other one to get how much I have in the second solution. So in the end, we know that they have to sum up to 1,000. So if you want to start by writing it like that, and then some of you jump right into the equation. Well, 60% solution of x plus 80% solution of 1,000 minus x is going to equal a 72% solution of the final amount. That's one way to do it. And you can think of this as like, this is the amount of mixture 1, this is the amount of mixture 2, and this is the result over here. That's one way to think about it, instead of using a table. But it's the same thing you would do with the table. With the table, we were putting like 60%, 80%, 72%. We had 0.6, 0.8, 0.72, x, 1,000 minus x, 1,000, and then we multiplied those two to get a number. Multiplied those two to get a number. Multiplied those to get a number, and said the sum of these has to equal this. Well, what are we really doing? We're literally finding out the exact amount of salt, and we're equating salt quantities. Right? If I have 60% salt solution, 60%, and I have 500 milliliters of it, it means that 300 of the 500 milliliters are actually just salt. Literally, 300 milliliters of the 500 milliliter solution is actually salt. Now, not necessarily a right way to form that statement because salt is not usually measured in milliliters, it's measured in grams, but the concept is that the proportional amount of it is 60%. So here, we can think of it this way, or we can go right to the table, either one. But it's the same solution in the end. Now, if I did this with a table, here's what it would look like. You'd have the amount of acid on the far left. So we had 60%, 80%, and 72%. So we'd say, okay, well, how much of each of these are we going to have? Well, we're going to have the amount of 1,000 milliliters of the answer. We don't know how much we have of this one, but we know that this one is 1,000 minus whatever that one was. Now, if we take the actual salt percentage and convert it to an actual decimal, we don't have to make a new table, a chart column for this, but I've done that in the past. And then we multiply these two quantities together every time. That's what we're getting up here. We're getting 0.6x, that's coming from here. That's this part of the equation right here. And then 0.8 times this gives you the middle part of the equation right here. And then finally 0.72 times 1,000 gives you the last part of the equation. And that's the part over here on the far right. So in the end, what are we doing? We're saying, well, you know what? This is literally the amount of salt. Okay, this is the amount of salt physically present in the actual mixture. 0.6x, 0.8 times 1,000 minus x. So we're going to add these. Well, I'll circle them. We're going to add these two together and set it equal to this. And that's what this equation up top is giving us right here. The rest of that you should be able to solve on your own. That equation is pretty simple. I would multiply by 10 maybe to start to make numbers easier. Is that if it helps you? Okay. How would this change if instead of given what we were given here, we were told the following? So let me just slide this down for a little bit. Let's see how this works. All right. So instead of giving this information, let's change things up. Ready? So I'm going to change, and I'm going to tell you that you have already 450 milliliters of this solution. All right? That's the only change I'm going to make. We've got 450 milliliters of the first solution. And you want a solution of 72% salt. So how much of the 80% solution should we add to the 450 is the question. How do I set up this problem? How does it look different than the last one? So you're given the amount of salt solution of part 1. You need to figure out how much of part 2 you should add to that to get a total of 72%. I don't know how much solution you're going to have at the end. It doesn't matter. But the question is, how much should you add of the 80% solution? Go.
You could have like x as the 80% and for the 72% you could have x plus 150.
Very good. That's literally all that changes. That's it. X is what's unknown now. X, the unknown, 80% solution. How much of the 80% do we add? Unknown. How much? Well, the total is going to be 450 plus x right there. So all that changes is my numbers here. So this 0.6 doesn't get multiplied by x anymore. It gets multiplied by 450. This 0.8 gets multiplied by x, not 1,000 x. Then this 0.72 multiplies by 450 plus x. So all I'm going to change are my volume in my table, or just these numbers here. So this would change to be 450. This would change to be x. And this would change to be 450 plus x. And if I don't see that right away, or if you guys don't see that right away, take a look at the table here and see that all that would change would be the volume. This would be a set 450 milliliters now. This would just be x. You're just trying to figure out how much of this there is, x. And this final part here would be 450 plus x. So all of these would change. This would change here, this would change over here, this would change over here. We have to change all those values. But I want you to see how it's the same exact problem, except instead of not knowing how much of the final solution, or how much each individual solution should add to get a specific final solution, now I'm giving you one of the initial solutions, and you have to find out how much of the other to add to it to get a final solution of some percentage, acid or salt or whatever it may be. Good question. What else? Remember, these are a function of what you ask. Completing the square. We'll do a quick example. That's a good one. This is definitely on your test. So you could have any quadratic, right? So let's start with one. We'll make it a tough one so we can see that we can do this even when it's difficult. 2x squared plus 5x. I'm not going to go that hard. Let's make it 6x plus 7. Let's do that. Equals 0. Completing the square. Who wants to take over from this point? Completing the square. What do you got? How do we complete the square?
Use AC method.
You could try AC method for factoring, but the question was, how do you do completing the square? You can definitely look for AC method. You're going to get what? 14. What numbers multiply to 14 give you 6? None do. So then you stop and say, all right, I can use the quadratic formula or completing the square. One problem on your test will definitely say solve by completing the square. What's that process? Anyone remember?
Is that the one where you have to like subtract by 7? In this case, subtract by 7. And just
You do have to get rid of the 7. Do you remember what I have to do after that or no? You definitely get rid of the 7 to start. So this is what you have here first. And you have to get rid of a.
Is it like something where you divide by 2 and then square?
Yeah, that's the one where you're dividing by half and then, or dividing by 2 and then squaring. But first you have to get rid of whatever a is. So let's get rid of a. So I'm just dividing everything by 2, right? Divide everything by a. Now we take half of b and square it. b is currently 3. We take half of 3, which is 3 halves, right? And square 3 halves. What do you get when you square 3 halves? What do you get when you square 3 halves? 9/4. Well, I'm going to add 9/4 here. I've got to add 9/4 here. So let me circle what I'm talking about there, okay? I added 9/4 to both sides. If I add 9/4 to one side of the equation, I have to add 9/4 to the other side of the equation. Well, 9/4 on the left-hand side is very convenient. The reason it's convenient, and this is not always obvious, so take a look if you don't get this right away, is because this will always factor into x plus whatever half of b is squared. That will always work. That's the note you want to kind of jot down. It's not obvious. If you try this out, x plus 3 halves times x plus 3 halves, this is what you'll get. Please don't just square both and say, oh, x squared plus 9 fourths. You're missing the middle term. You'd have to FOIL this out, right? If you FOIL this out, you get back up to the previous line. This always works out this way on purpose. Well, we have to combine the right-hand side still. 7 halves, I would think of as 14 fourths. Would you agree? Why would I think of it as 14 fourths instead? To achieve what? To get what? 14 fourths make me common denominator. So I'm going to end up with here negative 5 over 4 on the right-hand side and x plus 3 halves on the left-hand side squared. Well, how do I get rid of the squared? Anybody? Yeah, just root it. Now, when you root it, though, you're going to recognize that you have plus or minus always. And you happen to have the square root of a negative number here, which means you're going to have what kind of an answer? Imaginary. Very good. So completing the square is just like the quadratic formula in that it gives you your answer for your quadratic equation. I'm going to subtract the 3 halves, put plus or minus. Now, when I do negative 5 fourths, I first put an I. I can think of that as an I, right? And get rid of the negative. And then I'm going to write this as 5 over 2, like that. Take a look and see if you can make sense of that, please. Radical 5 is still radical 5, but the denominator is really radical 4, which is just 2. The I comes out because this was imaginary and it makes it positive inside now. Okay, now, if you were writing this in A plus BI form, it would be negative 3 halves plus or minus 5 over 2i. And the I would usually go on the right-hand side. That's like the traditional way to do it. But it doesn't really matter, but if you want to be traditional with when you see in like your book and stuff, the I would go on the right side. You could have used the quadratic formula. Remember, x equals negative b plus or minus the square, that whole thing? That's the only other way to solve this. So it's either quadratic formula or completing the square, one of those two. I shouldn't say I'm good because I don't know for a fact, but I'm almost 90% sure that I actually did both of those in the test. Like I give you a function and say solve with completing the square, that's this method. And then the other one might say solve but anyway, or solve with the quadratic formula. Okay? So this was from section 7-1. If you want to see more example problems in your notes, 7-1. What else? We still have about 5 minutes, I think, right? 46? We still got 5 minutes? Other stuff you want to go over? Chandler?
Like rules of exponents.
Rules of exponents? Okay. So let's go through some examples and quick rules of exponents. So let's start with, I'm going to just go through a few examples and we'll talk about the rules as we do them. So let's say we had x squared times y to the 4th over y to the negative 2 all to the 3rd power. And the question says, simplify and answer with all positive exponents. First step. What would you do first? What would you do first here? James, what do you think? What should I do first? There's more than one answer, so you can take either route. Okay, distribute it to each. All right, so if we take the 3 on the outside into account, what does everything become then? What does x squared become, James? And then y to the 4th becomes? And then the bottom? So you could start by distributing the exponent and remembering that when you raise a power to a power, you are multiplying those powers. If you forget that, think of this as x squared, x squared, x squared. That's what that is when we write 3. This is y to the 4th, y to the 4th, y to the 4th. Well, y to the 4th, y to the 4th, y to the 4th is y to the 12th. X squared, x squared, x squared is x to the 6th. So when you're doing these problems, if you forget your rules, don't worry. Just physically rewrite it. I would think of it this way again. Okay, that's how I would write the first part. Times y to the fourth 3 times. Then what do? If the question said with all positive exponents, Morgan?
Multiply it divided by 1 over y to the 6th to get the -6.
You're on the right track, but that's not exactly what you do. You wouldn't multiply the bottom by 1 over y to the 6th. It's not really multiplication that you're doing right now at this point, that you're trying to work with. It's not multiplication, really. Alex?
You would turn the negative 6 to 1 over y power 6.
Yeah, you would change it, not multiply it, though, right? So this would become this. That's what it really means. Again, a negative exponent is 1 over the positive. Well, when you divide by a fraction, you're multiplying by its reciprocal, really, right? So in the end, we're taking this numerator and multiplying by the reciprocal of this. The reciprocal of 1 over y to the 6th is just y to the 6th. So in the end, this y to the 6th ends up getting bumped up to the numerator, really. That's what happens. So really, if you want to remember a simple rule, when you see a negative exponent, move it to the other position and make it positive. Okay, it's the same thing as doing this over here. Because this whole thing over here would become x to the 6th, y to the 12th, times the reciprocal of this fraction right here, which is y to the 6th over 1. So in the end, I'm ending up with this and this all in the numerator. So I could have just taken this and moved it up to the numerator to start the problem. Okay, I could have done that earlier in the problem too. I could have possibly, if I wanted to, done it here. I could have taken this y squared, moved it up, made this y to the 6th. Then I would have 6 times 3, which would give me 18. Well, it's the same thing I'm going to get down here now, right? Then I end up getting, let's see, x to the 6th, and then this would be y to the 18th. Because this 12 right here, plus this 6 right here, will give me y to the 18th. Other exponent rules. Anything to the 0. Anything to the 0 is 1. Remember, anything to the 0. So something like this, right away, start by just crossing this off and putting a 1 in its place. Then we have b to the 5th over a squared b to the negative 4. And from the last problem, I'll remember, we'll just take the negative exponent and move it up. Leave the positive 1 down below. Take the negative 1, move it up. That becomes b to the 9th. Trying to think of other rules that we had. Subtraction, multiplication, distribution, negative powers. I mean, if you had fractions, it's the same thing. So if you had this, let's do an example like this. Well, what do I do? How do I complete this? Or how do I simplify this? My rule tells me that I should add the exponents, right? The rule tells me to add the exponents when I multiply these. So what would the sum be here? What would the sum be? How about I rewrite this, Will? So I'd have all denominators the same. What should I write the first one as? 2/4. How about eighths? X to the 6/8 and 5/8. 4 plus 6 is 10, plus 5 is 15, x to the 15/8. Bring questions tomorrow. You have 3 more days left now. Counting down, okay? 3 days of review. You have to make sure you bring questions tomorrow. Bring your old tests as well. Have them with you in class.